So, okay, it's on this side? No.
All right, so we are going to do 21.4, which is transforming exponential functions. So the last few days we've looked at, actually I think we have to check our homework, don't we? All right, so looking at the next section. So we've been working with exponential functions, and so we've looked at, how the graphs perform and how like different things affect. Yes, Joe. Yeah, we'll have one more. We'll have one more, and
We talked about this last week.
it'll be next Wednesday.
Actually, I'm going to try.
All right, so we are going to explore how changing parameters affect the graph of an exponential function and graph transformations of exponential functions. So we're going to look at the parent function for exponential functions and how different graphs compare to that parent function. So you can use transformations of the graph. So we have f of x equals b to the x to graph functions of the form a b to the x minus c plus d, where a and b are constants. A can't equal 0. B needs to be greater than 0, and b cannot be equal to 1. So we talked about if you have decay, then your b value is between 0 and 1. And if you have growth, then your b value is greater than 1. All right, so we have the graph f of x equals 1/2 to the x. So looking at that, is that going to be growth or decay? That's going to be decay because it's between 0 and 1. So let's bring up Desmos. So there's our 1/2 to the x. And then what's the equation that it asks us for comparison? So this for this growth for this decay function, this would be the parent function, and then everything that we do, just like we did with the other transformations of functions, for this one, our a value is how much? The second one. What? 4. Our a value is 4. So how does the blue graph compare to the red one? Our x-intercept here is 1, and our y-intercept here is 4. So that was multiplied by 4, right? And then what else do we know about our lines? Like here we have a point at -1, 2, and then at -1 we have 8. So what happened to those 2 points? To get from the red line to the blue line, what happened? We went from 2, put it away, went from 2 to 8. So from 2 to 8, what did we multiply by? 4. Multiplied by 4, right? So at -2, we have 4. So what do we think on the blue line? What do we think that's going to be? So when our exponent is -2, what's our output going to be? 16. So we multiply by 4, right? And if I go up here and then find -2, I'm at 16. So this multiplier in front, the 4, our a value, what is that doing to all of our output? It's multiplying it by 4. And we can, if I go down here, it's going to be the same thing. Whatever our output is, we multiply it by 4 to get to the blue. So here we have 0.5. So then what do you think the blue line is, our blue output? well, 1, because it'd be 0.5 times 4. So we have 1. All right, so then, so if we graph 3 to the x and negative 1/2 3 to the x, what do you think this negative 1/2 is going to do to our graph? It's going to cut it in half, and then what about that negative? What's that going to do? Right, so we're going to have a reflection of it. Now the 3, oops, is that going to show growth or decay? Growth. So our red line is our parent function. We have 3 to the x, so we have a growth exponential function. And then our negative 1/2, let's look at some points. So our y-intercept here at 0, we have 1. So what do we think the blue line? So we have our y-coordinate is at 0, negative 1/2. And then for this one, we have 1, 3. So what do we think the corresponding point on a blue line will be? All right, good. So we'll go to negative 1. Now it's at 1, negative 1.5. So it's all our points are going to be cut in half. Okay, so questions on what that a term is doing to our points? All right, so sketch the parent function. So now we're looking at, in the past, when we modified our x value and think about like with a quadratic, how were we moving when we added or subtracted to our x? Do you remember? Okay, so let's look at it. Was it x plus 3? What was our exponent? X minus 3. Thank you. All right, so what happened to our graph? Move to the right, and it moved to the right how many? All right, so here we're at 0, 1. If I go over here, I'm at 3, 1, right? So we moved, so if this is 0, 1 here, then this point to get up at a height of 1, we moved to the right 3 units. So what do we notice about the distance between our two lines? It's consistently 3 units apart, right? So then if I change that, the next one was what, plus 2? So how did that affect our graph? We've moved to the left how many units? 2. So here is our 0, 1, and then to get a height of 1, now we're at negative 2, 1. So our graph just moved to the left. So if we added 2 to our exponent, our graph moved to the left. And if we subtracted 2 from our exponent, it moved to the right. So if we did another one, if we had 2 to the x minus 5, how would that move our graph? Right, so if our exponent was x minus 5, then our graph would move to the right, that 5 units. So if we look at b, our parent function, we have 10 to the x. So 10 to the x minus 1. Okay, it's going to go 1 to the right, and then x plus 3 in our exponent. 3, 3, 4. So 1 right. So here, so now we're subtracting 1, but not from the exponent. So how do you think that's going to move your graph? Up and down. So we're applying our variable here, and we're going to get our answer, and then we're subtracting 1. So that's going to give us our up and down. So let's look at is it minus 2? Minus 1. So our red line is our parent function again. And so if we look at our y-intercept, that's the easiest point to see. So from here, we move down 1, right? So if it was plus, so plus 3, how would that change our graph? We'll go up 3. And so we'll go up 3. So it's a lot of the same transformation rules that we've learned when I dealt with quadratics and different polynomials. And so not a whole lot of change here, so it's the same rules that apply for exponents. And you're applying the change to your multiplying outside, so our a value multiplies our output by whatever. Any change on our x coordinate is going to move it left or right, and then a change like this after on our complete output, and that's moving it up and down. If our a value has a negative in front of it, then that's going to reflect it across our y-axis or x-axis. Let's see what else we have. So in D, we have 1/3 to the x and then 1/3 to the x minus 2. So how's that one going to change? So this one's going to go down 2 from our parent function. All right, and then the 1/3, is that growth or decay? Is this one growth or decay? Growth. All right. How do we feel about this? All right, so now we're going to combine them. So if we look at A, we have 3x plus 4, and then plus 1 at the end. Good. And so the 3, growth or decay? Growth, so we know our graph is going to start low and then increase. And then our plus 4, so that's our x-axis. Are we moving to the left or to the right? We're going to move to the left 4. So we have growth, left 4, and then the plus 1 tells us up 1. So we can do a table of values, or if we look at the on our parent function, if we had 3 to the x, we're always going to have a y-intercept there, because when we put in a power, 3 to the 0 power is always 1, right? Anything to the 0 is 1. So our graph would look like that. This one, from this point, we're moving to the left 4, so 1, 2, 3, 4, and then up 1, so now it's going to be here. It'll be a rough sketch, and then if we look at Desmos, we can get a nice, neat one. So looking at our y-intercept, we've moved to the right 4, or to the left 4. 1, 2, 3, 4, and then L1. Wow, it's exciting in here. All right, so we okay? All right, so what's happening with this one? So growth or decay? We have decay, so 1/3 is decay. Are we moving to the left or to the right at all? All right, so if we're moving to the left or to the right, where's our change? Is it in the exponent or after? In the exponent. So do we have a left or right change in this one? No, because our exponent's not changing. And then what's that -4 telling us? We're going to go down 4. And then we have a multiplier on this. So we have an a term. So what are we going to do to all of our terms? Multiply by 2. Forgot what it was, 1/3. All right, so we can see kind of how it's gotten deeper, and that's that multiplied by 2. And so we have this point here, we have our 0, 1, and then, so we're going to multiply that by 2. We're not moving left or right, so then we multiply by 2. So we have 1, that would give us 2, but then we're moving down 4. So from 2, 1, 2, 3, 4. So we can take any other point, kind of all blend. Was it 1, 1, 3? So we're not moving left or right. So if we take 1/3 to the -1, that gives us 3. Multiply by 2, which would give us 6. And then 6 minus 4. So the blue line should be at -1, 2. So do you guys want to practice graphing them or just move on? Let's practice graphing 1 and then we can move on. All right, so let's look at this one because this one has lots of stuff going on. So our parent function would be 4 to the x, right? So let's just graph this one real quick. So do we have growth or decay? We have growth, right? So we know our graph is going to start low and go high.
You go to the right 4, down 2, and multiplier.
Okay, good. Yeah, so once we get the parent function, then we can just kind of pick a couple points and then kind of do our order of operations to plot the new one. So let's do -1, 0, and 1, and that should be enough to get the gist. So if we do 4 to the -1, what's that number? 1/4. 4 to the 0, 1. And then 4 to the 1. so we have our parent function sketched. So now we're moving, all of our points are going to get moved to the, you said right, correct? Right 4.
Down to
Down to, and then we have that multiplier of 1/2, so all points times 1/2. So let's pick this point here. So we're going to go to the right 4. So 1, 2, 1, 2, 3, 4. And then, so 1, 2, 3, 4, thank you. Times 1/2, so I'm at, so then 2, and then down to 1, 2.
wait.
Alright. Because we're shrinking it and then we're moving it down. So now let's choose this point. So we're going to go to the right 4. 1, 2, 3, 4. So I'm at 1. 1 times 1/2 is 1/2, and then down 2, 1, 2. And then we had our point here, 1/4. So 1/4 to the right 4. So 1, 2, 3, 4. 1/4 times 1/2 is 1/8. And then down to 1, 2. So this one, so we've shrunk, so our points have decreased our multipliers by 1/2. We've moved everything right, then multiplied it, and then moved it down. So we're still maintaining our order of operations with exponents, and then multiplying, and then the addition and subtraction. So let's just go and check it, because we know that I make mistakes sometimes. So there's our parent function. Then we have 4 to the x minus 4 minus 2. Alright, that was close to what I had, right? So it's not terrible. It's not unlike a lot of the other transformations that we've done. We just have an exponent now. Now, what happens if this was a negative? What would that do to our graph? It would flip it. So it would get flipped across our, it would get flipped, bless you, vertically. So now instead of flipping up, now we flip it down. So just looking at number 4. So starting with our exponents, follow order of operations. So how's that? Well, we start
To the right.
Okay, so to the
5.
right.
And then multiply by 8.
Okay. So I get growth or decay. Growth. And then this is telling us that we're moving to the right 6. And then all of our points are going to get multiplied by -3. So the 3 means times 3, and the negative does what? Flips it down. And then we'll move everything up 5. And the one thing I wanted to look at when I was, our asymptote, our trump wall, here it's at 0, and then see how our trump wall, our horizontal asymptote, that moved down the -2 as well. And that's what we flipped over when I added that negative. It was the, so there's that, I think I can just cut and paste that. So when we do the reflection, we're reflecting across that trump wall, the horizontal asymptote. So let me just introduce this. We're not going to finish this today, but I want to at least start it. So looking at natural base exponents. So on your graphic, on your scientific calculators, you want to get those out real quick? Because you have the E button on there, so this will help if you're making a table. And if you are planning on going into business, this button, the number E, that will be really important. It's like 2.7 something. It's commonly used in finance and business and investments and stuff. And so that's where it's used. And so your E button is second, and then yours is the LN, so second LN. So yours is going to be same thing, so second LN. So second LN is probably yours. You just have yours right there. So yours is there, so you put your number in, and then yours is your reverse. Trying to find yours. Yeah, second LN. LN stands for natural laws. So this is all right. So we all found our E button, our natural base, and so we're going to graph that and then look at transformations. So let me bring up Desmos. So you can, so if we're looking at this table here, we can fill this in. So if E is 0, we can do E to the 0 power, which is 1. You don't need to calculate for that one. But then E to the 1 power is 2.7. And then E squared and then E to the 3rd power.
5.369.
20.7.
5.369.
All right, so looking at the graph of that, so we have our, so is that since E is 2.7, is it representing growth or decay? Growth. So we have growth. So which row of the table gives the approximate value of E? Which one of these has the value of E?
1.
So what kind of number does E represent? Well, and can we convert that to a fraction if you push the fraction button? Does your calculator do anything?
27/10.
Oh, we'll just do the E button.
Second.
Trying to do it upside down, it's not working.
Second LN.
And then just do at 1. And then if you push fraction, does it do anything?
No.
No. So is it rational or irrational? Irrational, because I can't represent it as a function. So it's an irrational number. Alright, so complete the table below, so this is everything that you guys just did, plus some. So if you do E to the -1, What's that?
For the 54 point five.
This one? For square? I thought it was 7 point something.
No, it's 3. Because it went 0, 1, 2, 3.
It's 1, 2, 3.
Wait.
It has negative 1.
Oh, I was going. Oh. We're going to the next one. Oh.
So e to the negative 1 is
0.3, 6, 7, 8, 7, 9, 4, 4, 1, 2.
Alright, and then I forgot what was e squared. 7 point. And then e cubed. That was 20.08. Alright, so then it asks us to graph these three on the same coordinate plane.
No.
So since e is 2.7 and that's in between 2 and 3, how do you think the graphs are going to look? All right, so they're pretty close, right? So we have let me move these. All right, so we have our blue line was our 2 to the x, and then our red line is our e, and then our 3 to the x is our green. So our e to the x, how does that compare to our 2 to the x and 3 to the x? So it's sandwiched between them, right? And is it closer to the 3 or to the 2?
3.
It's closer to the 3. And then the decimal 2.7, is that closer to 2 or to 3? It's closer to 3, right? So, our numbers are, they're always in between. I don't know how else to explain it. So since the base is between, the graph makes sense that the graph is between, right? So compare, what number do they all have in common? What output? 1, right? When x to the 0, they all equal 1. All right, so looking at number 4, we have our parent function e to the x, and then we have g to of x equals negative 1/2 e to the x. So what do you think that negative 1/2 is going to do? What's the 1/2 going to do to our output? Times it by 0.5, and then the negative is going to flip it, right? And so it's going to flip it across that asymptote. All right, so we look at our y-intercept, here we're at 1, and here we're at negative 1/2, and we flipped across that y equals 0, since that's our horizontal asymptote for our parent function, that negative 1/2, all of our, we can see the distance, you can really see it over here where it's half, the distance from the asymptotes, the red line, it's half for the blue line. Questions? Asymptote. All right, I think we'll stop there for today.